Okay, let's talk about rates of radioactive decay. First thing you need to know is that rates of radioactive decay are first order kinetics. And if you're unfamiliar with that, go back and look at my video on first order rate laws, because that's what we're going to be applying for this particular process. So if you look at the KSA of radioisotope strontium-90, look at the amount in grams. If we start with 10 grams, after one half-life, we'd say we're about at 5 grams. And then after 2 half-lives, we're at 2.5 grams. At 3 half-lives, we're at half of that. 4 half-lives, we're even half of that. And we keep going, progressively smaller. A lot of times after 10 half-lives, they say it's gone. Maybe that's not a hard and fast rule, but it gets below the limit of detection if you get too far below that. So if we look at this one's pretty straightforward. What percentage of cobalt-60 remains after 15.81 years after it's initially made? Cobalt-60 has a half-life of 5.27 years. So we're just going to look at straight half-lives as opposed to pulling out first-order rate equations. But we can certainly do that. So if we look at our first-order rate law, we know our time was equal to 15.81 years, where t sub 1/2 was 5.27 years. We just need to figure out how many half-lives that represents. We can do it with the calculations, but we just need to see how many. So what ballpark are we in? How many half-lives is that? Is it even? So if we take 15.81 divided by 5.27, we divide that out. So that's equal to 3 half-lives. Pretty exact. And if you end up exactly on a half-life, you can just kind of work it. So that means I would divide it through by half 3 times. And the problem doesn't really state an amount I start with. So let's just say I've got 100% of my radioactive sample. And so 1 half-life I divide by 2. Okay, but I got 3 half-lives. So I can divide it through by 2 3 times, or 2 cubed, which is 100 divided by 8, which means I would have 12.5% of my original sample left. That method will work if you're on an even half-life, but past that you'll have to resort to first order kinetics. So looking back at it, if we're not on even half-life, you're going to have to use first order kinetics. Remember, radioactive decays are independent of temperature, which is a difference between that and chemical reactions. So the rate of decay is equal to Ka, or one version of the first order rate law, ln of A0, which is the initial amount divided by A, which is the amount at the current time, equals Kt. You can algebraically rearrange these a couple different ways. The K is dependent upon the half-life, as we mentioned in the Kinetics chapter. So the half-life is equal to the natural log of 2 divided by the K, or the other way around. A lot of times we're calculating Ks for rate law equations, so really the other way around sometimes is more useful. So here's the same question 15 years after it's initially made, half-life 5.27 years, same exact information, except now instead of being at 15.81 years, it's 15 years. So I'm not exactly on a half-life, so I'm actually going to have to work the problem. Okay, so let's look at this on paper, we can see the previous example above where we got 15.81 years, 5.27 year half-life. We found out that was exactly 3 half-lives, but now we're just a little off of that. Should end up close to that, but not quite. That's not a linear relationship, it's a logarithmic relationship. So we have to keep that in mind. This was the equation I just gave you, but in its more traditional form, it is a little better for calculating the final amount. Where this one would work better if you wanted the time. But we need the K from the half-life. I told you that solving it for K was a little bit better or more useful, I guess is a better word, than this, because you more often are calculating K's for rate equations than calculating half-lives. So we get ln of 2 divided by 5.27 years. So our K is going to equal 0.131 years to the minus 1 power, running that through your calculator. So then we just do a little plug and chug. Ln of A equals negative K, 0.131 inverse years times 15 years plus ln. And our initial amount we'll just say was 100%, like in the previous problem. We run all that through our calculator, and we get that is equal to 2.63. So solving for A, that's going to be E raised to the 2.63, which will give us 13.9%. You compare that, it's a little bit shorter of a time, so you'd expect a higher percentage, and not by much because the time's not off. But it's maybe not quite what you'd predict if you tried to make it a linear relationship, though. So make sure you're using the first order kinetics equation. All right, let's look at one more. This is a little bit different problem because we want the activity in Curie's. We can get it in becquerels, and we will during the middle of the problem. But it's a little bit different, and so instead of using the integrated rate law, we're going to use the more straightforward rate law. But we have a K, which is given in this case instead of the half-life. But if you were given a half-life, you could calculate. But K, 1.25 times 10 to the negative second inverse seconds. We want to know the activity of 1 gram of that radon 220 in Curie's. So let's go to the paper. Before I can really work this, I'm going to need to work the radon 220, figure out how many atoms there are. So the rate is equal to K times the number of atoms. I need to know atoms disintegrating per second. So if we got 1 gram, radon 220, so we got 220 grams of radon per 1 mole. Radon, this is way back when we were doing stoichiometry, but it's still a useful calculation. 1 mole of radon is Avogadro's number, 6.022 times 10 to the 23rd radon atoms. So grams cancel, moles cancel, we're left with atoms. We're going to have to run that through our calculator. And we get 2.74 times 10 to the 21st radon atoms. That's a means to an end. Let's plug that into our rate law. 1.25 times 10 to the negative 2 seconds to the minus 1. We got 2.74 times 10 to the 21st atoms of radon. So multiplying that out, we get 3.42 times 10 to the 19th. That's atoms disintegrating per second. So that's actually our becquerels. Then we just need to convert. And there's 3.7 times 10 to the 10th becquerels per 1 curie. I did that exactly backwards. Curies, becquerels. Sorry about that. And so we're going to divide that by 3 times 10 to the 10th power. Get that in scientific notation. We're going to get 1.14 times 10 to the 9th curies. And that would be our answer.